Thank you. I'm very pleased to be today, and very happy to present you my presentation about how we can do an approach to do like complex analytics, like fast Fourier transform, using a Kafka stream or KSQL DB. So first of all, Kafka stream is a technology which is based on a Kafka client API. It's a more higher level abstraction, and it allows to create K-stream and K-object abstraction based on the topics. And KSQL DB is a more higher level abstraction, which is allowed to do declarative way of defining your K-stream and K-table. So as we know, Kafka, Confluent Kafka, it brings the static world and moving world together. So I mean static world like classical databases, and Kafka, we can create a real-time databases. And now we bring it together, and basically what happens, as we say, no silos anymore, right? Because we can take all static databases and connect them with connectors to Kafka topics and create a snapshot of the static world in the databases in our Kafka topic. And after that, we can do many things like joining, enriching our streaming data with the data which we do look up. Instead of going to the database, we're just using K-table, which stays in memory, in RocksDB, and we enrich our K-stream. So Kafka stream processing level of abstraction, it's our Kafka client API, Kafka stream, KSQL DB. One important thing to know is the difference between K-stream and K-table, right? K-stream, it's a sequence of moves. It provides immutable data. Once it's in the topic, you cannot change it. And table provides immutable data. And a very important thing also is duality between K-stream and K-table. How we can go from K-stream to K-table. We can do aggregation, windowing, which is another way of aggregation, and joining. And how we go from the table to the stream. We create a stream on the same topic, which is support K-table in memory, and we provide CDC content data change, which starts generated all upgrade particular primary key records in K-table. Now, what if we could treat streams as waves? What I mean by this, if we look at analytics in Kafka, and in general, mathematical analytics, right? There are several levels of complexity using Kafka. First simple case is just queuing. So we're decoupling producer and consumer, and we're passing event from producer to consumer processing. So it means we're processing events as a particle, right? The next way is aggregating. So we try and kind of do simple analytics. So we do average, minimum, maximum on a whole event, life of event in real time, or on a window, again, because window is just way of aggregation. And the next level is, so windowing. So we can provide aggregated function based on a some window. And more complex way, it's a window with the aggregate function collection list. So what's this collection list? If you came from the static database world, right? In the static data world, we have a table with the attribute A, B, C, D, X, Y, Z. If we do aggregate function, we just say select A, and then we use aggregate function, count, minimum, maximum, average, from table group by A. And we cannot add B because we will get error, right? There is only one column which we are grouping allowed to be in the select statement. So output will be a single row. With analytic functions like Oracle Analytics, MS SQL, it provides this notation over partition. So in this case, you will get in the whole table output, and there will be another derived columns where you can see average rank of each of your records. And that's a very powerful thing to do analytics. And there are, luckily, the same analogy exists in Kafka Stream and KSQLDB with aggregated functions, collection list, collection set, and others. So if we look generally on the usage of Kafka, so it's two main classes, right? It's a business, like finance, insurance, healthcare, and Internet of Things, which is, we presume that it is some signal processing, like we have a sensor which takes some measurement and provides you a signal of wave signal. And we also know this motto that streams are everywhere. But what if we can say that waves are also everywhere? So, for example, if someone say, I don't need your analytics because I work in the business, right, or insurance. I'm just taking my data, take some window, do aggregation function, and that's it. I can give you some example. For example, in shipment business, if I'm shipping something, right, in order to do complex predictive shipping analytics, let's say there are main key metrics in the shipment. It's called how many orders in your distribution warehouse currently in processing. The lower this number, the better, right? So you're getting some inbound stream of orders, which customer orders something. You have to fulfill this order and ship as soon as possible. So when order events arrive inbound into your system, it increases your metrics. So you are all more orders which must be fulfilled and shipped. Once you shipped, it decreases your number of orders in process. So if we look at it, so we will see that it's kind of create a wave, right? You send some orders, the wave increasing, you ship, it's decreasing. So now you have a wave, it's like a derivative data or the characteristic of your streaming, right? Stream is everywhere, but there is some hidden characteristic inside that, which is a waving. That's we can say waves are everywhere. Now, if we have this wave, again, I can use analytics to analyze behavior of this wave. That's why. And this motto, waves are everywhere, it goes very well with the analogy in physics, wave-particle duality, right? Similar to our Kafka Stream table, stream duality. You know, in physics, in the beginning of 19th century, there was developing this theory that wave and particle could exist together. So if you have some like electron source and you emit an electron as a particle, you can see result interferation as a waves. So this analogy is described very well, I think, our stream in Kafka, when you stream data. So you can mine this data from these shipments, waving, you can catch this wave and then do some analytics on it. That's why you need wave analytics. And the best way to use wave analytics is a Fourier transform. You know what's for Fourier transform? It's the way to go from the time domain series, if we have some signal, right, to go to the frequency domain. So basically you get in the frequency, you decompose your complex wave into sum of frequency with particular amplitude, magnitude. So basically, any signal in the world could be dissolved into multiple curves. Like in this example, right? You have 3 waves, and the red one, it's a superposition of all of them. So now let's try to create a system which will include a signal generator, where you can generate some signals with a complex form, and we broadcast them to the MQTT broker, Mosquito in this case, and then we connect Mosquito to our Confluent Kafka via connector. And in Confluent Kafka, we create a pipeline of small processors, and one of them will be user-defined function, which performs actual fast Fourier transform. And after that, we pick it up and do some step-by-step processing to pull out this information, frequency information from our complex signal. So in order to create a signal generator, it would be nice to use some interpretive language like Python, right? It's very simple to write this program, and then we say y equals, and then we just write any complex superposition of sines. Like in this example, sine x, which is 1 hertz, and then we subtract 0.5, half of the next sine, which is 2 hertz, 2 multiply x, plus 1/3, 3 hertz. And it's easy to use. So in order to use it, we can use a Jython, which is an embedded Python interpreter, which we can use in Java. We just define a Python interpreter bin, and then we pass this parameter, and we say execute. We import math library, right? And then we just call this formula, and we get the result. So, and then we create this in Java, and we create a callable pulsar class, for example, runnable, which sleeps for some number of seconds we need to simulate signal. And then we call callable sensor, which will pretending taking measurement using the Jython and upload it to the Mosquito MQTT broker using this Jython simple interpreter. And we configure MQTT broker with a connector, this configuration, which Kafka knows this connector, and we pull in this data from the Mosquito. And we have a MQTT source connector to pull data, InfluxDB syn connector. We're going to use InfluxDB as a database series which will be populated from the Mosquito to present our curves. And we can choose either Prometheus or InfluxDB. I more prefer InfluxDB. So we need this sampling. Sampling, it's a simple thing, right? We just have this curve, and we call this interpreter, and we're getting the result. Now, the beauty of the Kafka Stream and KSQLDB, it's the way of aggregating by the windowing. The simple window is a tumbling window. In this example, we have a 5 seconds tumbling window. And if we have a different sensor, green and blue, that goes to each different aggregated tumbling window. And now once we have this tumbling window, we collect it, we can treat it as a time series and perform some analytics. And those are aggregated analytic functions. It is collect list, collect set, histogram. So, and the other very important and very powerful thing in KSQLDB and Kafka Stream is KSQLDB lambda function. Once we got this collection list, it's nice to use this lambda function like a transform, reduce, filter, so we can manipulate our x and y values. Now, the better way to use, instead of tumbling window, to use a hopping window. Hopping window, it has a time interval as well as sliding window. In this case, we have 5 seconds timing window and 1 second sliding. It means every 1 second passed, we create another, the same size tumbling window. And now each event which occurs at a particular time will be synced in all these windows which are active at current time. What does it allow to do? It allows that we don't want to react on each event coming to the window to do some analytics. We want to accumulate all the window and then emit final. Instead of emit change on each event, we want to react on emit final when the window is closed. But if your window is pretty big, then you will have some latency to do this analytics. That's why we need hopping, so we can slide 1 second, and on each seconds we do analytics calculation Fourier transform every second, so we can refresh it more frequently. So Fourier analysis, we're going to use Java Commons, and this Java Commons library provides you class which you call. You send the array of data x, and it will convert to the Fourier transform. But in reality, Fourier transform is not that simple. You not just call it and you're getting the result. You have to do some additional handiwork. And that includes, for example, like in this case, when we're passing this signal, 0.8 plus 0.7, etc., and we want to call this Fourier transform. And in this case, we also add additional random signal for noising. So we need to do several steps. First, we need to call this Fourier transform, and you will get this result, which shows all this noise. And as you can see, it's symmetrical. So you see the data on the left, which is the same as on the right side. So that's how Fourier algorithm works. So it means once we're getting the result, we need to manually take this array and divide this mirror by half and takes on the left side, which shows the graph below. After that, we need to change amplitude with the frequency peaks, and after that we need to transform our original signal to retrieve exact amplitudes. And that will be our final solution. So it includes multiple steps which we need to program and do. And we do it with the beautiful KSQLDB lambda functions, transform, reduce, and filter. So in this example, we can take collect list, our time, series time, right? And collect list as a values. So we'll get into array T and V, which represent our graph original. And now we can do transform T, for example, to cast it to the varchar, because later we need this to merge these two arrays together into the key map, and key could be only string, right? So we do as map T varchar and magnitude, and it will be a dictionary of our points. And now once we get these points, we can filter these points, and the lambda function for filtering for the dictionary, you have to provide two parameters, key and v, key value, and then you specify lambda function v greater than 0.4. So it means all the value which is above will be filtered out, and we are excluding our noise. Oh gosh, I should do something broken. Okay. Okay. So basically, we have this timeline with all this signal, right? And the sample coming as a points x1, y1, x2, y2, etc. And we define the window, hoping window in this example of one of our window. And with the collect list, we are collecting all points into one array, x and y. And then we define user-defined function, and we call this user-defined function, which is user-defined functions. It's a function which you can write with the particular rules required for the API, user-defined function API, and you can upload to your KSQLDB cluster, restart your cluster, and you will get a new extension functionality for your KSQLDB. So you can just go select FFT, the name of your user-defined function, and you pass the array, your collection list Y, and you'll get a result Fourier transformation. And this is example how you do user-defined function. You define description of your function, and you provide the this is API for the defining your function. So you're passing list input, and you're getting output back. And here is shows additional things you have to do. For example, when you sending an array to your user-defined function to perform, to call the Java common map library Fourier transformation, you have to pass array which is 2 power n. So it means you need manually, depending on your array, you have to add additional array with the 0 values. Otherwise, your call Fourier transform will raise an exception. So you need to do this additional step. And then you take this jar and you put into this folder with your Kafka SQL server properties, and you define this parameter KSQLDB extension. Yeah. So now how we can implement it with the KSQLDB. So there are several approaches how to implement it, obviously. So you can use Kafka Stream API low level, or you can use Flink. But in my opinion, the best way to do it just as a proof of concept to use KSQLDB. And it's a good approach because KSQLDB based on SQL, and you can give this job to any analyst, and any analyst knows SQL, right? So they can write this KSQLDB. It might be not optimal, not very fast, but it will work, and then the developer can pick it up and transfer and port it to the Kafka Stream API and do it working much faster. So first thing, we'll create a stream, and that stream will generate this data on the right side with this JSON. The unique number sensor ID, it should be unique and should go into the key, because when we're sending it to the Mosquito MQTT broker, Mosquito MQTT broker requires unique sensor ID. And then it has some timestamp and dimension, which like a tag, which allows you to search by a particular curve. If you have multiple sensors and you go to the multiple partition, then there will be multiple sensor in each partition, right? And value will be value. It could be multiple values also. And now the main part, we create a waves window table. So we create table, provide always parameter, and now we're using this beautiful aggregate function collection list. We collect all timestamp, we collect all values, and we do window hopping with 20 seconds, advanced for 2 seconds, and group by name. So it will be 2 grouping now, right? By name, so by the sensor ID and by window. And important thing, we want to do emit final. Remember, we don't want emit changes here, so we don't want to react on each event dropping in the window. And when we create this table, we will see this result on the right side with this JSON, and it will be produced every 2 seconds for the particular 20-second window. So we'll have a number of samples, 1,500 in this case. Sampling interval, so we're getting value every 10 milliseconds or 100 sampling per second. Time as array and value as array, which value is the value of our curve. Now, the next thing, once we got this table, so the table is the main agent which will compress all this data, 1,500 records, representing sampling for each curve. If you have a many sensors, right? It will be compressed into one record, and each record will contain 1,500, in our case, sampling. So now what we have to do, we have to manipulate and massage this data in our pipeline, which we need further, right? And here is this K-stream, K-table duality come for help. So we are creating stream on the same topic, as you can see. This table was created on the wave window topic, and we create now stream from the same topic, wave window. So it allows stream to generate this event which produced by table to be able for us to process it further. And now we are going to several steps how we do processing it. So first we so we're taking this array T, we call first Fourier transform our user-defined function, and we're getting array Fourier on the output. So on the right side, we see the result, time and Fourier. Now we need to take this t, transform to the subtract of the Unix time start of our window, so to normalize our time. The next step, we do this computation, so we take transform each of time to the frequency. So in order to do that, we need to determine the delta frequency and then number of samples multiplied by Castaneda's double Unix time divided by the time vector. So we're converting time millisecond to the portion of frequencies. And Fourier, we have to transform divided by number of samples and divided by 2. So we're normalizing our value of frequency, Fourier transformation, to the real amplitude, magnitude of our signal. And then the next step, we transform time to the character, and now we can merge our time and value to the map as map, varchar as points, and now we can filter all this noise and getting, so each of these steps, taking events from the topic, does some transformation, and sync the result into intermediate topic, wave step number 6 in this case. And then we need to, again, split our map to the 2 array. So we do map keys as time and map values function as amplitude. And final step, we filter out. So now, in order to see our data in FluxDB, we need to transform the format of our data from MQTT broker to the format which accepted by InfluxDB. To do that, we create stream, and then we use this nice SQL function, insert into select from, which allows to do multiplexing. When you have multiple streams and you want to send them and mix to the one output stream, you create several persistent query, insert into our destination from select from each of our sources stream. And at this point, we do transformation of the message. Sensor and formula as a text. So in FluxDB, it provides tags and timestamp and values. And that's it. Any question? So I have some demo to show. If I exit from this. So I have a Confluent Kafka running on my machine. And here our topic we created, waves. And Let's start some generator. So here is generator with a sine x. It start producing x, y value, which is sine. You can see it negative, positive. Messages. Come on, where is messages? Just here is our Mosquito MQTT broker. So sensor one we uploaded to the Mosquito. Why don't I see messages here? Wait. Sorry for delay. Just a second. Let's start 10 more. So we have 10 generator running with a different sine amplitude. Still, I don't see anything. Why? Connector must be down. So here is the broker. You see all signal from 1 to 10 sensors, and connector. Oh, connector not started. Just a second. I started connector in flux. And we need flux. Okay, 2 connectors running. Topics, so the data is flowing. Here is our science. So we have all processing, the data is coming here, and the final step. So the final will be refreshed every 2 seconds. And now here we have, so here. So in the original topic, we had 1500 array of time. And here we converted to very few, x and y. So basically we have x as a frequency. We can say 6767. It will be one frequency, and it will be corresponding to the amplitude of about 1 magnitude. So basically, we had 1500 records, and we compressed the data into very few records. And that's the beauty of Fourier transformation. So that we can take original signal as a time series, and we can go from time domain to the frequency domain with very few value. So in cases, for example, if we're somewhere on the edge and we're taking sensor information, millions measurements per second, we just convert it to the very few numbers, send it over internet, and then we can reconstruct our signal to the real curve on the other side using reverse Fourier transformation. And that's about it.